Prvých vrcholov dnešného podujatia Noci výskumníkov. My tu máme naozaj špičkových ľudí, ktorí vám budú prezentovať fantastické veci. Tohoto vedca, ktorého uvidíte teraz na pódiu, toho sem nedostanete len tak, pretože je to špičkový vedec z centra vesmíru. Je to výskumné centrum vesmíru z univerzity v Leicesteri. Je to vo Veľkej Británii a naše poďakovanie patrí veľvyslanectvu Veľkej Británie a Severného Írska, ktoré je na Slovensku, pretože kontaktovali tohto špičkového vedca a podarilo sa dostať ho sem, aby nám prezentoval. Je to odborník na vesmírne lode Apollo, je to odborník na vesmír a je to ten, ktorý veľmi pútavým spôsobom bude prezentovať, ak vás zaujíma táto hornina, všetko vám poviem. My už sme tu mali prednášky o tom s týmto pánom, s pánom profesorom, prečo si môžete urobiť vodu vo vesmíre, ale veľmi ťažko na Marse. Mali sme tu váhu mesačnú, to znamená, že ste sa mohli odvážiť a ukázala vám, koľko by ste vážili na Marse. No ale teraz sa budeme venovať iným vesmírnym záležitostiam. Dámy a páni, privítajme tohto špičkového vedca tak, ako ho vieme privítať my. Privítajte ho potleskom a nenechajte si újsť jeho prezentáciu. Dámy a páni, práve teraz prichádza špičkový britský vedec John Holt.
Thank you. Well, thank you very much for that introduction, and good evening to you all here in Bratislava. I was here this morning, and it feels really weird having a catwalk to walk up like this. I feel like I should be in some sort of French fashion show showing off the latest Italian underwear or something, but fortunately for you, that's not the case. So my name is John Holt, and I'm from the University of Leicester, and I'm going to talk to you a little bit about some of the work that I'm doing, developing tools and instruments for the European Space Agency, hopefully so that we can go back to the moon. I'll also talk a little bit about the future and where I see some of those things going. This picture here is from my hometown in Great Yarmouth, and I just thought I'd show it because I just want you to get an idea of what it was like when I was the age of some of you people here. When I was growing up, there were no mobile phones. Technology was very different. There was no Google, there was no email, there was no internet, Twitter, and all of the things that we take for granted today. And I could never have imagined that the university where I now work was doing space science and space instrumentation. And this picture here is what we call a sounding rocket. And back in 1960, when Professor Ken Pounds joined the university, he started doing space. And the university started developing technology for going on to rockets. And I had no idea that this was happening just 150 miles up the road from where I lived. I just want to point out one character. Oh, the laser pointer doesn't work. At the front of the rocket is Dr. Jeff Hoffman, and he'd done his postdoctoral research at the university in the physics department where I now work. And it was known at the time he was probably destined for greatness, and this picture here is taken from STS-61 in December 1993. Now, at this point, I was 19 years of age, and those of you that are clever and quick at mathematics will be able to work out how old I am today. But even at this point, when I was thinking about my career, I had no idea that we were doing space in the United Kingdom, and the university where I now work had been a part of training an astronaut who would be repairing the Hubble Space Telescope. And that's why events like this are actually really important, because it exposes young people, and not just young people, but older people to, to science and technology and mathematics. So just going back a little bit further, 1969, I wasn't born then. That was when we first set foot on the surface of the moon. And I'm not going to talk a great deal about Apollo, because you know all about this. And you can see Buzz Aldrin there having his picture taken by Neil Armstrong. I'm just going to go through a few pictures very quickly. And just like all good holidays, they had to come home back to planet Earth. And on the right-hand side there, you can see the Eagle ascent stage approaching the orbiting spacecraft around the moon. I find it interesting that ever since mankind or humanity climbed out of the trees and learned how to make tools, we've been making hammers, and on the moon they took a hammer with them. And it just so happens that I have a replica of the Apollo hammer here. This was a vital tool, even though it's incredibly simple. You've all used one, but in order to do science on the moon and take rock samples, you probably need something like this. And you can see here on the left-hand side the Apollo hammer stowed away in the spacecraft. And then on the right-hand side, in Apollo 12, you can see the hammer being used to knock a pole into the ground. Sadly, in 1972, and I still wasn't born, okay, we stopped going to the moon. And so I kind of feel that my generation has missed out a little bit, and that makes me a little bit sad. I should just say that some of the details about the Apollo hammer are very hard to come by. And when I say details, I mean detailed engineering about exactly how the machining was done, the materials that were selected, how they were treated, surface finishes, and all of these kinds of things. And I'll talk a little bit more about that in a moment. Fortunately, for my generation, and now your generation as well, the European Space Agency and NASA want to go back to the moon. And they want to use this as a bit of a staging post for then going on to Mars. And that's where a lot of my research is, in a field called astrobiology, and looking for evidence of life, the evidence of life on Mars. And we've wondered back at Leicester, do we need to use a hammer like this? Could we develop a mechanical device? And what are some of the problems associated? And I'm just wondering if I can get a volunteer to come up on the stage for a moment. Go on, I saw your hand go up first. Come on, there's some steps just at the back. Give the gentleman a round of applause. Come on up. Okay, what's your name?
Daniel.
Daniel. Okay, so Daniel would you like to be an astronaut?
Yes.
You would? Okay, so we're going to train you as an astronaut. So here is your Apollo hammer, and this is the sort of thing that you would use if you were going to the moon. So you've just stepped out of your spacecraft and come with me, and here we have a rock. I don't want you to hit the rock very hard, but I want you to go slowly through the motions of knocking a piece off of the rock. Okay, can I stop you just there for a moment? There are a couple of problems actually with Daniel here. He's in a spacesuit, so the bit on his back is going to be very, very heavy. So if you're leaning over like this, the chances are you will fall over. So don't take this personally, but I'd like you to go down on one knee. Go down on one knee. There you go, just one. There you go. You will never see an astronaut on two knees like this, because it's going to be very difficult to get back up. And if you were to fall over as well, because you're a bit unstable, then you might get dust all over your spacesuit. And if you get dust on your spacesuit, that changes the thermal properties of your spacesuit, and that becomes a problem. Okay, now you're in a good position, and I'm going to come down with you. So very slowly, I want you to go through the motions again of taking a sample. Okay, maybe swing the hammer a bit. Okay, hold it just there. Freeze that frame. What is the problem with this particular situation? You're an astronaut on the surface of the moon, and just here you've got a helmet, and you're in risk of hitting your helmet, and that's one of the big problems of using a hammer on the surface of the moon. Daniel, thank you very much. You'll make a great astronaut. I'm just going to show you a video here because I was doing some research out in the field. Actually, it was in a mine 1.2 kilometers underground. So this is in the UK, just off the northeast Yorkshire coast. And there should be some volume with this. And the gentleman that you can see there working with me is called Dr. Matthias Maurer, and he is a German astronaut with the European Space Agency. And although the volume didn't work there, one of the things that he's just said is that if you're using a hammer on the surface of the moon, it would be a really bad day if you were to knock your visor, because you would probably die, actually. And the next slide. So I mentioned that we want to go back to the moon and use that as a bit of a staging post for eventually going to Mars. This is a picture from the Encyclopedia Britannica back in 1957, and this was all that we knew about Mars. We could see some dark patches and some light patches, and we didn't really know what they were. Was it vegetation? Was it lakes? And then in 1964, when Mariner 4 took the first flyby images, we could see a little bit more detail. We could see some craters, but that was really all that we could see. Fortunately, NASA have had a series of rovers and landers, Viking 1, Viking 2, Pathfinder, Spirit, Opportunity, and now Curiosity. And we know that the surface of Mars was once warm and wet. We're not talking about today, we're talking probably 3.5, 4 billion years ago in the past. A time when life was perhaps only just thinking of getting started here on planet Earth. Mars was warm and wet. And so we have to wonder, did the same processes happen on Mars? Could life have gotten started there? And in this image here, you can see evidence of water. You'll notice there's two big boulders in the background. They probably have a mass of something like 1.5, maybe even 2 tons. And so they haven't just blown there in the wind. There's been some major water event, hydrological event, which has delivered those boulders. And a bit further down, you can see bedding. These are the kind of things that you will have seen and maybe not really thought about, but certainly evidence of water activity on the surface of Mars. Now, one of the reasons that I probably didn't go into teaching, and fortunate for young people, is I like to give people homework. And I'm going to give you people some homework as well. When you go home tonight, or maybe over the weekend, I'd like you to go into the garden, pick up a rock, ideally a sedimentary type rock, and break it open, and look inside, and you will find evidence of microbial life living inside. This is a type of rock that I've been using in my laboratory. It's a sandstone from Montana in the United States. And you look at the top there on the right-hand side, it's just like any kind of rock, a bit like this rock we've got on stage perhaps, the sort of thing that you would just kick around and not give it a second thought. But look at the rock a little bit more carefully. Underneath the external surface, you'll see a green layer. And you might think, green, does that suggest that something is living there? Well, I can tell you that yes, you would be right if you thought that. And it's a type of cyanobacteria, and collectively, we call them cryptoendoliths. Crypto, because you can't see them, endo, because they're just under the surface, and lith, because they're inside of the rock. And so for this reason, we don't think it's unreasonable that if Mars was once warm and wet, and if microbial life actually once got going, maybe 3.5, 4 billion years ago on Mars, that it too would have lived inside of the rocks. And microbes live inside rocks because of the same reason that we live in houses. It protects you from the environment. So if we're going to go and explore Mars, and we want to do astrobiology, and we want to look for evidence of life, then perhaps we want to be able to look inside of the rocks. Now, NASA have been doing this, and certainly on Curiosity at the moment, they've got a drill that can drill into a piece of rock. I've got a piece of rock here. I'll pass it around in a moment for people to touch and feel. This is not from Mars. This comes from a quarry about 10 miles from my university. I use this rock in the laboratory because it's very similar to what some of the tougher rocks we think we might find on Mars. And you'll notice that I've drilled some holes into the surface of this. And I would absolutely love the day when GA drilling can go to Mars and go a little bit deeper. But these holes are only 10 millimeters diameter, and NASA can only drill maybe 50 millimeters deep. We want to go a little bit deeper. Now, I'm going to need another volunteer. Can I get another volunteer from the audience? One more volunteer, go on. There's somebody at the back. Gentleman here with the green hair. Come on up. So, what's your name?
Matthew.
Sorry?
Matthew.
Matthew. Okay, Matthew. Can I call you Matthew then? That's right. Okay, excellent. Right, so what I want you to do is I want you to pretend that you are a rover, okay? And so if you were to, I don't know, maybe go down on all fours, actually. On all fours. Like, okay. You haven't got arms and legs anymore. You've got wheels, okay? And one of your arms is a robotic arm, and I want you to hold this, okay? Right. Now, the scientists in Mission Control have identified this rock here as something really interesting. Maybe it's a Mars sample return mission, and they want to bring a core back. So we're going to send computer commands to you to tell you to drill into the rock. But you can't actually see that, as in the scientists can't see what's going on. So I want you to be honest, and I want you to close your eyes, and very carefully, I want you to put your arm forward, and I want you to have a go at drilling into the rock. You are now on the rock. Have a go at drilling. Okay. Can people see what's happening there? Carry on, Matthew. What's happening to the bit? It's walking over the surface of the rock. Okay, you can stop there. You've been absolutely fantastic. Thank you very much. Cheers. The people that make the drills for NASA, Honeybee Robotics, have built some amazing drills for going to Mars. But drilling on Mars is extremely difficult. And at Leicester, we've been wondering, is there something different that we could do? And this is what we've come up with. It's called SPLIT, the Small Planetary Linear Impulse Tool. And you can see from the photo there, it's a little bit smaller than the hammer, and I can assure you it's a lot smaller than the drill that's on Mars at the moment, which weighs about 29 kilos. But before I tell you a bit more about this, oh, what happened there? There we go. Okay, I'm only going to show you one equation tonight. We don't need to worry about the detail of the equation, but that equation tells us about this situation here. And some of you may have had this. I hope it didn't happen to anyone coming here tonight. But the adults, you're driving along the motorway and a stone flings up and it hits the windshield and you get a little bit of a chip. Now, what you tend to find, if you don't do anything about it, and particularly in winter, over a period of time, the crack grows and it grows and it grows. And it happens because of vibration and temperature. But rocks are very similar to a piece of glass. You know intuitively, if you had a piece of glass and you kept knocking, the glass will eventually break. We can do the same with rocks as well, because they are brittle materials. They're very strong this way, but in terms of what we call their fracture toughness, they're not very good. So this is Split. It's a collaboration between Natural History Museum, National Space Academy, and the UK Centre for Astrobiology, which is based at Edinburgh University. And I just want to mention one of those collaborators, who are National Space Academy. That's an organisation that does pre-university education, and they teach A-level maths, physics, and BTEC with a space context. And one of the things we do at the University of Leicester is we actually get young people involved in doing research. And I'll show you some pictures in a moment of some of my students doing that. And we're not talking about university students. Okay, so this is the mechanism that's inside here. It's very simple, and it's a motor and it's a spring. So we're using electrical energy to store potential energy in a spring. And you can see what happens when we get to the end of the cam. The hammer shoots forward. I've got a rock here, haven't I? So we put this up against the rock, and when the mechanism gets to the right point, it shoots a weight forward, the hammer, that hits an anvil, and it's just like a sculptor with a hammer and a chisel, going bang, bang, bang. And we're not doing massive blows like a hammer, we're doing it gently. And we're actually exploiting a thing called low cycle fatigue, and we're trying to induce brittle fracture. This is a video that I made a couple of years ago. It's a bit of an older video, it's an older prototype, but it shows you exactly how Split works. So here's a piece of that rock, similar to the piece I showed you. I'll pass it around in a moment. This is a very hard rock. This rock is actually used for building, or used to be used for building. And notice that the tip is on the surface. We're applying our high energy impulses, and over a short period of time, we're able to make cracks grow bigger and bigger, and eventually you can predict what's going to happen. And I got very excited when I was doing this test. It went a bit slower than you can see here. The piece of rock that just fell away is the size of your hand. Those little holes I just showed you in the other piece of rock, if Curiosity was drilling those on Mars today, it would take about 90 minutes. To break away a piece of rock the size of my hand or my fist, we can do that in 3, 4, maybe 5 minutes. And I want you to notice something else. The tip never made contact with the fresh surface of rock. So this piece here that's highlighted by the yellow circle, it's pristine. On the surface of Mars, if you'd done that, that piece of rock would not have seen the light of day maybe for 4 billion years. There's no dust on it, and there's no risk of cross-contamination. If you made an interesting discovery inside that piece of rock, you would not have to argue the case that you had taken it there because there was contamination on your drill tip. The tip never touches it. So I'll just show you this video here, and hopefully the sound will work. I think we have a problem with the sound because this worked last night. So this is actually back in Bowlby. And you can see here, the last film you saw was done in the laboratory, but there's nothing like doing field testing to find out all the little snaggets, if you like, inside your research. Can we have a look and see if the sound is going to work for the next videos, please? Okay, so I'm just going to show you a couple of pictures here. So people like me, we don't go on holidays to fancy places like Florida and other such exotic places, except Bratislava, of course. I consider this a bit of a holiday. Back in 2016, the UK Space Agency sent me to Utah in the United States, to the desert. And you can see here, in this environment, it looks very much like the Mars pictures that I showed you. What we've done is we applied split to a rock, and very quickly we were able to break a piece away. And when we'd done that, this is what we found inside. So a piece this size came away, about 2 liters worth of rock. And the surface you're looking at is this kind of size. And you will notice at the top are signatures of cryptoendoliths, remember microorganisms living just below the surface. And the light sandy material, that's pristine, that's unchanged, it's uncontaminated. And the darker material is probably some sort of contamination from water. So if you were a microbe living inside a rock, you'd probably want to live in a place somewhere between the dry and the wet zone. Now, do a little bit of a thought experiment with me. If you were aliens coming to Earth in 4 billion years' time, you know, you send your rovers down, you're like, we found a rock here, let's drill a hole. Right, they don't talk like that. If you were to drill a hole just over here, you probably wouldn't find anything very interesting. Drill a hole where I've drilled a hole and bring your sample back. That's where you're most likely to find telltale signs of microbial activity. That's where you'll do your interesting science. And so one of the arguments that we're making at the University of Leicester is for future Mars missions, break the rock open first and then have a look inside and decide where you're going to do your drilling. Now I'm just going to show you a couple of images here. In this example, what we're able to do is take a slice of the top of the rock off. It was about this thick. Then we take off another slice. And we can do what I call geological triage. So we can look inside and say, is this an interesting piece of rock? No, move on to the next one. Or yes, it is. And so we're going to stay and play, and we're going to do some science. And you can see here, do you remember I said to you that the Curiosity rover can only drill down 50 millimeters? Well, to do good science, you want to get as deep as you possibly can inside the rock. If you were using split with a drill, you can knock off 60, 70, 80, maybe 100 millimeters. And then you can do your drilling inside, particularly if you want to bring that rock back. And I'll just show you one more picture as well from my holidays. These are my holiday postcards, by the way, holiday photos. I was really excited about this rock, actually, because if you found this on the surface of Mars, you'd be thinking, under the bottom there, that's where any organics may have been protected from radiation. They may have been protected from the environment, the dust, and other things. And I could see this little tiny crack, this little tiny fissure in position 1. And I speculated that we could use split to make that crack grow a little bit more. So getting a wedge in there and making it grow. And sure enough, we did. And a great big lump of rock, this size, after about 2 minutes, fell away. And I was absolutely just jumping around and beside myself with excitement. You know, because being over here is like Disneyland for a geologist. If you were to do this on the surface of Mars, you would get excited because you would drill hole 1 first, because you're going really deep into the rock. Remember, this has been protected from the environment maybe for 3-4 billion years. And then just for the fun of it, you might take a second core sample as well. Okay, holidays. Last November, the European Space Agency were very kind to me, and they said, John, do you want to go to Lanzarote? You look really bored in your laboratory. We want to get you out into the field. And it was a part of a program called Pangaea, where they're training astronauts. Now, that's Lanzarote that most people are familiar with. And this is Lanzarote where I was, and there wasn't a cocktail bar for 10 miles. So, again, Disneyland for people like me. When I was in Utah, that was analogous to Mars. When we're in Lanzarote, that's analogous to being on the moon. So the rock is very, the rock is very basaltic, very volcanic-like. And this is actually a picture of the back of my head. Never realized my head looked like that. And you can see me over here doing some work actually with National Space Academy, because they actually funded a bit of this field work. The gentleman with the green scarf at the back is Dr. Matthias Maurer, who you saw in a previous video, and he's an astronaut with ESA, and so we were training with him to try and instruct him on how to do field geology and field science. And we should have a video. And there should be a video coming up any moment now. Here we are. Now you can go to the ESA website and you can watch this video. There's a whole series of them actually, and you can download it and you can see the kind of stuff that we're doing. Lanzarote, no cocktail bars. Here we are on day 1, preparing for the field work. If you took the blue sky out of that and made it black, it would look like the moon. And when you're walking around, the rock is very, very much like the moon. So there were people from all over Europe doing this. And there's split being used to take a sample, and then going into an instrument to be analysed. So eventually, when we do go back to the moon, this is maybe the kind of science that we want to be doing. But in order to do that, you need to rehearse, you need to test, and you need to do it again and again and again, and make sure that you get it right. We're inside a lava tube here, which is a bit like a cave. We see these on the surface of Mars, and we see them on the moon. And if you want to be looking for evidence of previous life, or even maybe microbial life today on Mars, you want to be looking inside the caves. You can imagine being an astronaut that you're on an orbiting space station, or perhaps you are on some sort of or inside some sort of forward operating base. Here we're testing mapping technology, because if you're going to send a rover inside here, you want to know where you're going, you want to know where you're taking your sample from, and you want to know how to get out. in reality, an astronaut is probably not going to go inside a cave like that, certainly not for the foreseeable future, because it's going to be very dangerous. I could really do with a glass of water. This is where we're using split inside the lava tube. Now, although I was there last November, when I saw that video, I got really excited and the hairs stood up on the back of my neck. Not because I'm ever going to be an astronaut, because when I look at young people like you and when I look at my little nephews, I'm thinking that's the generation that are going to be going to the moon and doing this kind of exciting exploration. And there should be another slide. That's the same one. Okay. I just want to show you a couple of pictures because you didn't really see in the video what it was that we were doing. So this is actually a Google Maps image of where we were in Lanzarote, and you can see the cave that we went into. Come along. You can either send a rover into a cave like that, or you can send my PhD student, Adam. I'm sure he wouldn't mind. When we got inside the cave, this is what the walls looked like. The white stuff on the walls is a type of gypsum, if you like, a sort of a calcium carbonate or calcium sulfate. And that was as a result of the interaction of the minerals in the wall with the sea air. And then we went a bit deeper into the cave as well, maybe 50 meters. And you can see at the top there, that's the lava. And the crumbly material at the bottom, that's where the lava, when this volcano erupted, the lava rolled down a hill and it was rolling down the soil. And what I wanted to show with Split was that we could systematically decide exactly what sample we wanted. And that's why I've numbered them. So we took sample number 1. We then took sample number 2, 3, and 4. And we've done all of that in an hour. Amazingly, the samples fell butter side up when they fell off of the wall. And you can imagine that your rover might have an arm that would pick up those samples, put them in a box, and take them to the astronaut who's in his forward operating base somewhere. Or it might put them into a spacecraft and then launch them up to the orbiting space station where you are. And just for good measure, I decided to take a little hole, a core sample. At the University of Leicester, we're not just looking... Oh, thank you ever so much who brought this. Amazing. We're not just looking at developing technologies for use on the moon and use on Mars. And I mentioned Mars sample return earlier on. NASA are actually doing this at the moment. It's called Mars 2020. A rover is going to go to Mars. It's called a caching rover. It's going to take samples. It's going to put them into a box, leave them on the surface, and then a subsequent mission will go and pick up that box and bring them back to the Earth. And at Leicester, we've been developing technology for handling those samples. But before I do that, you may recognize these pictures. I've stolen them from the internet. On the right-hand side there is a picture from a film called Life. It came out last year, and I got so excited when I heard about this. It was a film all about doing Mars sample return missions. And for months before it came out, I was beside myself with excitement. You know, I was like, I want to go see it, I want to go see it. And then when I went to see it, I was a little bit disappointed because there was a lot of nonsense in it. And actually what's happening here, the British character, who's a biologist, he's put his arms into a glove box and they've brought an alien back from Mars and, well, there's some horrible things happen. The picture on the left comes from a film called Andromeda Strain. That's actually the 2008 version. I would highly recommend the 1971 version. You'll probably find it on Netflix, absolutely amazing. But notice they're handling materials inside a glove box, and they're using robotic arms to do all of the science. Watch these films, they're great entertainment, but it's Hollywood, and that's not how it happens. This is how it happens. At the University of Leicester, we're developing what we call double-walled isolators for handling these samples that will one day be brought back from the surface of Mars. And we're doing it because there are really two main considerations that we have to think about. Yes, there is the small risk, and it's a very, very small risk that you might bring back something that's maybe toxic or pathogenic. And so you want to keep it isolated inside a box. The cost of doing Mars sample return is going to be so big that each of your samples coming back are probably going to be, I don't know, £20 million or 20 million euros per gram. That's very expensive material. And so you don't want it getting contaminated with anything from the Earth. So you want the best of both worlds. Inside an isolator box, if you don't want anything getting out, you keep it negative pressure so that things can only ever leak in. But remember, we don't want that. If you want to keep it pristine, you don't want anything leaking in. Then you want to keep it at positive pressure, a bit like a balloon. We've developed a technique using, the laser pointer doesn't work, we've developed a technique and a technology with the European Space Agency and Thales Alenia Space. This wall at the back, which is an intermediate space, we hold it at positive pressure with an inert gas, in this case argon, so that anything leaks in, then it doesn't cause contamination. I mentioned National Space Academy to you earlier on, and here are two of my students, Matthew Clark and Hannah Coleman. They were working on this double-walled isolator, which was only delivered in March of this year. So they were my summer work experience students, and they're both, they're probably 16 or 17 years of age. And if there are people here from academia and industry for that matter, I would strongly encourage opening up where you can aspects of your research and your technical development and getting young people involved doing hands-on stuff. I even get my students published on papers so that people are exposed to science and technology and engineering and mathematics and the stuff that is exciting, the stuff that we need for the future. At the very beginning, I said that at the University of Leicester, we have been doing space now, space research, and putting stuff into space since 1960. And I'm very pleased to report that we are still doing that today.
-50. Normalize all switches. -10. 9. 8. 7. 6. 5. 4.
From the University of Leicester, thank you very much, and I hope one day I'm going to see some of these young faces doing exciting stuff like this. Thank you.